just out of curiosity, how many of you have had exposure to radio diagnostics of any kind? Okay, so significant fraction. Nevertheless, I'm going to kick off with slides with way too many words, unlike David's, which were works of art in terms of brevity, but carrying lots of information. But it's basically to remind you of some terminology and some ideas before we get into emission mechanisms and on into radio phenomenology and what we can learn using radio waves to study the sun, the interplanetary medium, and of course, astrophysics more widely. So Craig showed you a spectrum this morning, either the electromagnetic spectrum, which covers many, many decades in wavelength or frequency or photon energy, whatever your preference is. You see the optical slice there is only about an octave, a factor of 2 in wavelength. And for our purposes, the radio regime comprises all the wavelengths longward of about 1 millimeter or so, or a frequency of less than, say, 300 gigahertz. This is where the Rayleigh-Jeans approximation is valid, which we'll get into in a moment. And frankly, the technologies used to make observations at radio wavelengths share commonalities through this wavelength regime. But you'll notice that even with this definition, we're talking 7+ decades of wavelength. And we use them all, from millimeter, sub-millimeter even, all the way out to kilometer wavelengths at the edge of the solar system. So as I threatened, don't read all these words. It's to remind you of some things that I'm sure you've encountered in courses on radiative transfer. And later, if you've read Rybicki, Lightman, you've been exposed to the basic ideas of emission mechanisms and so on. But I wanted to remind you that what we seek here is to quantify this idealized quantity, the specific intensity, right? And it's defined there in that first expression in terms of a differential measurement of energy in terms of the specific intensity of differential area, time, frequency bandwidth, and solid angle. And the total flux is integrating over solid angle. And at radio wavelengths, we use a funny unit called the Jansky to measure flux density or spectral flux density. And it has awkward units. The SI units are 10 to the minus 26, very tiny number, watts per meter squared per hertz, okay? And it's even worse in CGS, ergs per centimeter squared per hertz. Specific intensity, attosteradian per steradian, okay? Now, with modern radio telescopes for astrophysical observations, we routinely get down to micro Jansky sensitivities, even tens or hundreds of nano Janskys. But the sun, just because of its proximity, is incredibly intense, right? So we don't just use Janskys, we use solar flux units, which are 10 to the 4 Janskys in one solar flux unit, okay? So if I use SFU, that's what I mean. Okay, specific intensity in free space is invariant. It can only change if there is absorption or emission or scattering. Again, you've seen these definitions before, the emission coefficient, the absorption coefficient, and we can write a simple transfer equation. The IDS is subtracting away a specific intensity through absorption or creating through emission. Now, we've already talked about optical depth. Craig mentioned it several times. We define it simply as the path integral over the absorption coefficient. It's a very useful idea. So we can rewrite the transfer equation in terms of specific intensity and the so-called source function, which is just the ratio of the emission coefficient to the absorption coefficient. Okay, here's an idea that maybe you're less familiar with. Black bodies have been mentioned. So systems in thermodynamic equilibrium for both the radiation and the particles can be characterized by a single temperature. And if that's so, then the specific intensity is characterized by this function B sub nu, the Planck function, okay? You've all seen it before. But what's kind of special about the radio regime is that H nu, photon energy, these are powder puff photons. They have very low energy relative to KT, the temperature characterizing the system in TE. So in fact, we can expand that exponential, and you have a very simple linear relation between specific intensity and temperature of the system, okay? So this is, are you all familiar with brightness temperature? It's a very convenient idea. It's basically the temperature, T sub B is what I've annotated it here, of a black body yielding the same brightness or intensity at a particular frequency that's observed. So it may or may not have something to do with the emitting system, but it's a convenient shorthand. It's a proxy for specific intensity. And let's face it, saying Kelvin is much less of a mouthful than ergs per centimeter squared per second per hertz per radian, okay? But that's what it is. And in fact, you can rewrite the transfer equation in terms of brightness temperature, effective temperature, which is defined in terms of source function there, and optical depth, okay? Very clean, very simple. For a uniform source, no background emission, you can solve that equation very simply. Brightness temperature is just 1 minus this exponential involving optical depth times the effective temperature, okay? So if the source is optically thick, that is tau much bigger than 1, the brightness temperature is just the effective temperature. It is a rather direct measure of the temperature of the system if it happens to be in thermodynamic equilibrium. And for certain solar contexts, it is. If it's optically thin, tau much less than unity, then brightness temperature is roughly the optical depth times the effective temperature. And all the microphysics is embodied in that tau or the absorption coefficient, okay? But it allows you to sort of sweep unpleasant details under the rug. Now, in reality, we don't measure this idealized quantity specific intensity. We try to get as close as we can. So, you know, cosmic radio sources observed by telescopes usually have some finite angular resolution. In radio astronomy, the jargon is the telescope beam. Okay, that's the resolution element on the sky, the pixel size, if you will. All right. So if we measure flux density, we gather up radiation with our reflector, focus it, couple it to a feed, amplify, measure, etc. That's our flux density, but it's the flux density that occupies that resolution element. Okay, so it's specific intensity times some realistic resolution. But if you just rearrange the equation, the approximation to the specific intensity is just the measured flux density per beam. So if you go to radio astronomy talks, you'll be hearing people chatter about flux density per beam or Jansky per beam and that sort of thing. Now, if we rearrange in the Rayleigh-Jeans approximation, substituting for I, the flux density is just given by this simple expression involving the resolution and brightness temperature and so on. We use it all the time. I haven't talked about polarization, and I'm not really going to dwell on polarization. It really is an important observable. I'm assuming most of you have encountered the Stokes parameters. We can, in fact, form all 4 Stokes parameters with radio telescopes by measuring using orthogonally polarized feeds, either cross-linear or RCP, LCP feeds. And you can, through correlations between all both of these, XX, XY, YX, and YY, form the Stokes parameters with suitable calibration. Okay, now I'm going to talk very briefly about emission mechanisms. I'm not going to talk, for the purposes of the sun and heliosphere, we don't really see lines. We don't see atomic transitions. We don't see molecular transitions. Certainly, for astrophysical sources, we do see these things, particularly molecular transitions, or molecular masers you've probably heard of, OH masers, silicon oxide masers, and radio recombination lines, which is the same thing as H-alpha, which is 3 to 2. But at radio wavelengths, you see things like 94 to 93 transitions, big fluffy atoms where the electron starts to cascade down the quantum number n. But we don't see them on the sun for reasons we can talk about later if you want. So I'm only going to talk about continuum radiation or coherent radiation, incoherent continuum mechanisms. And I think you've all encountered this. If you have a single charge, an electron, say, mass m, it requires acceleration to generate photons. And that's captured by the Larmor formula there. So acceleration squared gives the power ergs per second into some solid angle. The angle is given by that sine square, so it's basically a dipole pattern for non-relativistic electrons being accelerated perpendicular to their velocity. Total power just integrate up over solid angle. And you see that all other things being equal, that electrons are much more efficient emitters for a given acceleration. We can restate this in terms of relativistic effects. And you see, the q squared over 4 pi c squared, c cubed should be there, an acceleration squared, but these additional angular terms come in, as well as the Lorentz factor gamma, which are defined there. And the primary effects of relativistic effects are a boost in power and so-called relativistic beaming, or relativistic aberration is sometimes called. So you see that it leads to a forward beamed emission pattern. Okay, so how does this happen naturally? What accelerates charge in the sun's corona, say? Anybody? It's a plasma, right? We have free electrons, we have free ions. Think of the ions as being so massive they're effectively fixed for our discussion. So you have mobile electrons zooming around. What happens between electrons and ions? Bremsstrahlung, but why? What causes Bremsstrahlung? Exactly, a collision. So here's our ion, and the electron goes zipping by, and some impact parameter, and some microphysics has to deal with that impact parameter, but it feels a little impulse perpendicular acceleration as it zips by, and so it emits photons. Okay, so this is referred to as Bremsstrahlung for a plasma in thermodynamic equilibrium, thermal Bremsstrahlung, also thermal free. The particles involved are not bound. You can have non-thermal Bremsstrahlung, and it's in fact relevant to hard X-ray emission, right? Non-thermal electrons whack into the chromosphere and emit Bremsstrahlung very inefficiently. Even electron-electron Bremsstrahlung for relativistic or mildly relativistic electrons can happen. But for the non-relativistic case, thermodynamic equilibrium, the absorption coefficient is given by this mess, mostly involving lots of constants here. As I mentioned, impact parameter and the details of the interaction of the collision are hidden in these sort of Gantt factors here, which are temperature dependent, but because they're logarithmic, they don't enter strongly. But really the optical depth and the absorption coefficient are in the end proportional to column emission measure, temperature to the -3/2 and frequency to the -2. So pretty straightforward, pretty simple. And you see that for an optically thin source, uniform optically thin source, it doesn't really have a very strong dependence on temperature, unlike the kinds of EUV filter images that Craig was showing this morning. You have a very peaked response to plasma of a certain temperature range in the EUV, for example. So, take away absorption increases with column depth, decreases with increasing frequency or shorter wavelength. And the higher the temperature, the thinner the plasma. Okay? What's another acceleration mechanism in the corona? Just happening to be there. If there's a magnetic field, then there's a Lorentz force. And if there's a Lorentz force, the electrons undergo an acceleration, a continuous acceleration perpendicular to their trajectory, perpendicular to V. So unfortunately, there's different terminology used to describe this gyromagnetic radiation, sometimes called magnetobremsstrahlung, which is a mouthful. If we're talking about gammas close to unity and a thermal distribution of particles, we refer to thermal gyroresonance emission. Okay? Here, the temperatures are sort of coronal. We're not talking relativistic, but they introduce a slight distortion to the radiation pattern. And so if you take the power spectrum of the varying electric field, if you're sort of looking at the electron as it spirals around, you see it directed towards you, away, or towards, away. you sort of see a dipolar-like pattern if it's non-relativistic. If it's slightly more energetic, you start to get a distortion due to this relativistic effect. Take the power spectrum, and you get emission at harmonics, low harmonics of the electron gyro frequency. Okay? So in the case of the sun, typically, if you have a strong magnetic field, it renders the corona optically thick to gyroresonance absorption at harmonics of 2 or 3. Okay? So it gives you sort of a direct handle, not on the magnetic field vector, but on the magnetic field magnitude, the strength. Okay? What if we accelerate the electron a bit more? Then we get a more strongly beamed pattern. You get a more peaked electric field as it zooms in and out of the field of your line of sight. And if you take the power spectrum, you see that many more harmonics begin to appear. And what I don't show in the schematic is the harmonics begin to broaden. And as we get to higher and higher energies, we get higher and higher numbers of harmonics, up to hundreds, thousands, even millions. And they broaden and they form a continuum. Okay? So for mildly relativistic electrons, we refer to thermal and non-thermal gyrosynchrotron radiation, mouthful. So Lorentz factors of a few, so MeV electron energies. And if we go all the way to fully relativistic electrons, which are relevant to radio galaxies and things like that, we're talking, gammas of very large, tens of thousands, millions. The electrons are effectively moving at the speed of light, and this is synchrotron radiation. Okay? So I'm mostly going to dwell on thermal Bremsstrahlung and non-thermal gyrosynchrotron radiation. I'm not going to really talk about thermal gyroresonance emission, even though it's a very large topic in and of itself. These are both examples of incoherent radiation mechanisms, meaning you can formulate the contribution in terms of single particle interactions and then sum up over distributions, just integrate up, okay? But we also have coherent emission. And by coherent emission in this context, I mean the production of radiation involves collective effects, wave-wave, wave-particle, nonlinear couplings. And there are a couple that are important. They depend on two things, and Bob Ergen went into this a little bit yesterday. One is you need some source of free energy. And one of the obvious ones, one of the most productive ones, is an anisotropy in the electron distribution function. In other words, it's not in thermodynamic equilibrium. It has an anisotropy, some distortion to its distribution function in the angular domain for some reason. And the other is you need some kind of resonance, typically. And it just so happens that there are two natural frequencies for the sun's atmosphere. One is the electron gyro frequency, cyclotron frequency, and the other is the electron plasma frequency, which you've encountered several times in the lectures previously. And you can think of the electron plasma frequency as a natural frequency. It's an electrostatic oscillation. If you take a slab of electrons or fixed ions and pull it apart, let it go, there's an electric field induced. The electrons rush back towards the ions, overshoot, and so the restoring force is just the electric field, okay? But because the corona and the interplanetary medium have a finite temperature, the medium is dispersive. And so these plasma waves can propagate around. I'm not going to bore you with dispersion relations and so on, but you have a distribution, or can have a distribution of plasma waves or Langmuir waves, which are produced by a source of free energy, which can be, say, an electron beam, a shell distribution, or some other type of velocity distribution function, which has a gradient in velocity, which is unstable to the production of that particular resonant mode, okay? Now, in the case of plasma radiation, radiation that we detect with radio telescopes, these are transverse waves. How do you get from a longitudinal oscillation to transverse waves? Well, this is where the sort of nonlinear aspect of this comes into play. You can produce Langmuir waves, with these various anisotropic distributions, but then you need to somehow convert them into transverse waves. And this appears to happen in nature, mostly at the fundamental, that is the plasma frequency itself. The transverse waves are at about the plasma frequency, or at the harmonic, meaning twice the plasma frequency. The former requires scattering of the Langmuir waves off some low frequency source of turbulence or other source of waves. Ion acoustic waves are often invoked. But in order to have harmonic radiation, you need a secondary spectrum of Langmuir waves, and they need to coalesce head-on. Okay? And there's a vast literature in all this that goes back decades. Here's another mechanism that is thought to be relevant on the sun. And again, this was mentioned by Bob Ergen yesterday, namely the electron-cyclotron maser. So in this case, instead of, say, having a bump on tail instability or two-stream instability due to an electron beam, remember, magnetic loops on the sun, in another context, the magnetosphere, are converging typically. And so if you have energy released somewhere up in the magnetosphere, in the corona, fast electrons with a pitch angle distribution go down towards the atmosphere. Those with small pitch angle precipitate out. They hit the atmosphere and are removed from the distribution. The rest reflect, but now there's an absence of electrons at small pitch angles, and you have this loss cone distribution. And you have a nice perpendicular gradient in the velocity or momentum distribution. And that's the source of free energy. And the resonant frequency is the electron gyro frequency. Okay? So this one is a kind of a direct amplification mechanism. It's called a maser because it's really negative absorption. And it's, again, it has a history. I would say, it's probably relevant to the so-called solar spike bursts. I'll talk about dynamic spectra in a moment. But there's certainly very good evidence that it's relevant to terrestrial auroral kilometric radiation that Bob talked about, Jovian decameter radiation, and even certain stars. Brown dwarfs, oddly enough, turn out to be maser emitters, cyclotron maser emitters. So do certain DME stars, dwarf emission line stars, and even these big jumbo chemically peculiar A-type and B-type stars. So it's an important mechanism astrophysically. All right, types of observations. Well, the simplest thing you can do is simply measure flux density of a source at a particular time, at a particular frequency. And this has been done since the birth of radio astronomy. It's done at Penticton at 10.7 centimeters, and it's a valuable data set in and of itself because it's a proxy. It's tightly correlated with EUV. So the aeronomists, the people who study ionospheres, the ionosphere, are interested in the time series of these measurements because it represents several decades of the waxing and waning of the solar cycle and the EUV incident on the top of the atmosphere producing the ionosphere. We can go a little bit beyond that. We can record flux density at a particular frequency as a function of time, a light curve, right? This is done, at the Riston radiometers. This is the Air Force's radio solar telescope network. So it does 24/7 monitoring. Discrete frequencies, the Nobayama polarimeters in Japan do the same thing, but they do it in both right circularly and left circularly polarized radiation, hence the term polarimeter. And there's an example of a Nobayama set of discrete frequency light curves in total intensity above at 1, 2, 3.75, 9.4, 17, and 35 gigahertz. So nice flare. And below is the corresponding polarized emission, Stokes V. And you'll notice that this is opposite in the sense of polarization to the stuff up there. I'll leave it to you to think about. We can talk about later why that is. And, okay, we can take it another step forward. And this is sort of goes back to the beginnings of solar radiophysics. Namely, we can measure flux density or polarized flux density, both as a function of frequency, a spectrum, and as a function of time. You can think of it as a whole stack of light curves with very high spectral resolution. And this we refer to as a dynamic spectrum. And this was the tool used in the early days to identify the classical radio burst types, type 1, 2, 3, 4, 5. It's been a mainstay ever since. It continues to be actively used. Okay, well, we want to make pictures too. It turns out you can make images of the sun just like any other astrophysical source. Here's some examples from different telescopes. The VLA at 21 centimeters on the left. At 6 centimeters, that required something called mosaicing. Nobayama radioheliograph at just under 2 centimeters. all the way up to 1.25 millimeters with ALMA. Sun looks like the sun, but with obvious, interesting features on the disk. And ideally, in a perfect world, we have the technology now, and people in all wavelength bands are moving in this direction. We want to do imaging, broadband imaging spectropolarimetry. We want to combine all of these different ways of recording the specific intensity, the polarized specific intensity, into a sort of 4 to 5D observable. Okay, radio instrumentation, I'm not going to say very much. For these simple observables, flux density, light curves, dynamic spectra, typically we want to see the whole sun. It's a big and bright source. We don't need lots of collecting area. So we just have little dishes, which operate at fixed frequency or have a spectrograph attached to the back end or whatever. Okay. If you want to do imaging, though, because the resolution goes as lambda by d, and we're talking about long wavelengths, even with the old Arecibo telescope, 305 meters across at a wavelength of 20 centimeters, you had 10 pixels across the source. I mean, it was 3 arc minutes. You can't really use single dishes to make images unless you have, say, a focal plane array, which is still you're limited by resolution, or you have, or you just raster this great big thing. That's not really feasible, and there are way more elegant ways of doing it, which is to basically break your big aperture apart into little dishes, and then through correlations between those dishes, you measure the Fourier transform of the sky. Okay, so what an instrument like the VLA does, which is pictured down here, it's not a solar dedicated instrument, but you can, in fact, observe the sun with it. It measures the Fourier transform of the sky. I'll show you sort of what the distribution of points is like, the distribution of Fourier components, but you can think of the basic element of an array is not a single dish, it's a pair of dishes. Okay, and each pair is measuring some angular scale in the sky, which depends on the separation of antennas and the orientation of those. So you have for, say, VLA, which is 27 antennas, n times n minus 1 over 2 is 351 Fourier components instantaneously. And because you're measuring a complex quantity and the observable is real, it's Hermitian, you get twice that in terms of populating your aperture plane. Okay? Now for the sun, it's always moving, right? You saw that from the fabulous movies this morning that Craig showed and others have shown. You know, in astrophysics, things don't move very fast. A radio galaxy changes on a inverse Hubble time or whatever. So it's you can have all the time in the world to let the Earth rotate, and as the Earth rotates, those antenna pairs trace out a track in the aperture plane, and you can fill it in and do quite a good job of building up your aperture, and then the Fourier transform is your lens, and then you get your image by inverse Fourier transform of the measurements. For the sun, because it's always moving, you really don't have that luxury. I mean, it has its intrinsic activity, it rotates perversely enough, so you can't, things will smear out if you integrate up too long. So you really need excellent snapshot imaging coverage. So that means lots and lots of little dishes. So an example of such an instrument is the Nobayama radioheliograph, this middle one, in Japan. It's now defunct, unfortunately. It went for about 20 years, operating at 17 and 34 gigahertz. But you see lots and lots of little antennas with small apertures so they see the whole sun at once. And I'll show an example of a flare observed by this instrument later. And then sort of go driving towards this ideal of getting everything all at once, all the time. There's this Pathfinder instrument in Owens Valley called the Expanded Owens Valley Solar Array. It's only 13 antennas. It's going to be upgraded to 15 next year. So the imaging fidelity is not terrific, but it does sweep from 1 to 18 gigahertz in less than a second. So you do get this brightness temperature spectrum, and so you have a spectrum as a function of place in time through the source. Okay. All right, so that was my whirlwind tour of sort of preliminaries. And now we're going to sort of talk about radio emission from the sun and heliosphere. And then for the second part of the talk, I'm going to sort of turn things around and say, well, okay, suppose we have a source of very well-known properties, can we use that as a probe of the foreground medium? Okay, so using propagation of radio waves through the medium to learn something about that medium. In our case, the corona and the solar wind, although it can be used as well for planetary atmospheres and ionospheres just through occultation of that beacon, for example. Okay, so this is a vast topic. It could be a course in and of itself. The phenomenology, the physical environments in which radio emission occurs and can be usefully observed, and we can learn something about the medium in the physical process. I'm only going to touch very quickly, very lightly on some examples. I hope to convey the sort of flavor of the kinds of things one can do at radio wavelengths. And so I'm going to talk about emission from the quiet sun, specifically the chromosphere, using ALMA. I'll say a little bit about flares, which are near and dear to my heart. Coronal mass ejections in the classical radio bursts, and then finally the solar system boundary. So it's a lot, and then we'll talk about propagation. So I've sort of put up things schematically in terms of instruments at the various sort of decade by decade of wavelength. You'll see that there's a hash mark there that refers to the ionospheric boundary that Bob Marshall talked about yesterday. It can be useful if you have, VLF signals that you want to reflect off the underside and propagate around the world. But if you happen to be a low frequency photon outside the ionosphere, good luck getting through. You're blocked. So for very low frequency and long wavelength observations, we need to go above the ionosphere and use space-based platforms. So I'll talk about that a little bit. But let's sort of step through, loosely speaking, going from short wavelengths, high frequencies to very low, we're peeling the onion. We're going from chromospheric heights up into the corona, the outer corona, into the interplanetary medium, and all the way out to the boundary of the solar system. So you can sort of see it all across these 7 decades. This is what the sun looks like. On the left in H alpha, you've seen this many and many times. Probably you haven't seen a full disk image at 450 microns. This is 0.5 millimeter, basically. And what we're seeing, basically, remember what I said, for optically thick emission, brightness temperature we observe is basically the effective temperature of whatever's doing the emitting. This is the chromosphere. We're seeing basically a map of the temperature of the chromosphere. Okay. So, I think of millimeter, submillimeter radiation is highly complementary. To date, we've relied primarily on optical and UV spectral lines to try to make sense of the chromosphere. But they're tough. Spectral lines, they generally form under conditions of non-LTE, non-local thermodynamic equilibrium. And that introduces complexity in how you're going to interpret these lines. You have to worry about the rate of transfer, which can be complex, involving resonant scattering, partial frequency redistribution, non-equilibrium ionization, because things move on a timescale shorter than they can recombine or be ionized. So it's very complicated, and the models are marvels of computational creativity, but they're also, involve a lot of physics. And in contrast, it offers something like ALMA offers a powerful complement, because as we discussed, the millimeter continuum forms under conditions of LTE, thermodynamic equilibrium, and we're in the Rayleigh-Jeans regime. So we sort of have the simple linear thermometer when we're optically thick. There are complexities I'm sweeping under the rug. And the rate of transfer is pretty straightforward. We're not dealing with lines, levels, resonances, and so on, which is good because, let's see if this will work. This is a beautiful Hinode image going from G-band, showing the photosphere fading into the chromosphere, which is a nightmare of complexity involving, non-radiative heating, waves, shocks, transition from low to high ionization state, transition of dominance of gas to magnetic pressure, and so on. It's an extremely complicated layer. And you've already seen the confusogram in the lower right, which tries to summarize some of the myriad complex phenomena that occur. Well, I'm just going to zero in on one example. Craig showed you some spicules this morning in an image. This is an old phenomenon. They were discovered in the 19th century by an Italian priest, Secchi, also mentioned by Marco. But we were limited by the resolution available with ground-based telescopes, and everything was done in the optical. But that changed when Hinode was launched. We could see, calcium-2, for example, up in space with very high resolution and time resolution. And with the launch of IRIS, we could also do the same with ultraviolet lines, which you could measure temperatures of material in these spicules. And so there's been a recent resurgence of interest, so much so that some authors have even sort of interpreted spicules in a broader distribution of eruptive events, jets, jetlets, part of an ecosystem that loads the corona and ultimately the solar wind with mass and heated plasma. So we had a look at this with ALMA. On the left is sort of a limb image of spicules at 3 millimeters. In the middle is SDO AIA, and you're seeing the spicules in the foreground as dark. They're absorbing because they have neutrals. And then the IRIS magnesium-2 on the right. And we basically, looking at the spicules on the limb, they're optically thin, okay? And for a fixed brightness temperature, it turns out that the density is just proportional to T to the 1/4, totally insensitive to the temperature of the material. So we see all the plasma that is going to be in the spicule. And our conclusion was that there's not enough there, not enough mass flux being carried up to make a substantial difference in the energy budget of the corona. Okay, that's one example. Let's move up in wavelength to centimeter wavelengths. This again has a very long history and a very rich history. It can be used for many, many different types of phenomena, ranging from quiet sun to flares. There are several different emission mechanisms which are relevant here: thermal free to gyroresonance emission to non-thermal gyrosynchrotron. I'm going to talk very briefly about flares. Okay, so there's been again, that's sort of complementary to another techniques that's been used for many years, namely X-ray observations, and we've gone through many generations of hard X-ray instrumentation. Most recently, RESI, the Ramadi high energy solar spectroscopic imager. But up here in the corner is an example of light curves in microwaves and hard X-rays at 2 different energy bands, and you see that more than a passing resemblance. And there's a tight correlation between peak flux densities between microwaves, say at 17 gigahertz, and hard X-rays. So you often hear people say, well, they're great because they're looking at the same electrons, same distribution of electrons to produce the emission, the non-thermal gyrosynchrotron emission. And that's true, but they have very different dependencies on the ambient plasma density, on its temperature, on the magnetic field strength and orientation, about the electron distribution function of fast electrons that produce the gyrosynchrotron emission. Okay? So here's a cartoon that's been around. It's useful as a framework that I'm going to use today, simply to sort of orient you on the kinds of observations one can make. So something goes bang up here in electron acceleration, particle acceleration site. The electrons stream downward, and at the foot point, I mentioned pitch angle earlier. Those with small pitch angle, more closely aligned with the field, stream out of this magnetic bottle and hit the chromosphere and produce hard X-rays or whatever. Also thermalize and produce hot, soft X-ray emitting plasma, which they use the unfortunate term ablation, sort of backfills the loop that you see very brightly lit in soft X-ray imaging. Okay. A convenient model to think about this is the so-called trap plus precipitation model. It's very old, but it captures a lot of the features that we see. So fast electrons injected into this magnetic bottle, some linger for a while until they're scattered into the loss cone and are lost, and others promptly precipitate. And a mechanism that at the very least is going to scatter electrons is just Coulomb collisions, which I think Marco showed the other day goes as energy to the -3/2. The faster the electron, the longer it's going to sit around before it gets scattered. So you sort of see an evolution of low-end the lower energy electrons flattening out as they're lost from the trap. Okay, here's an example of a flare observed 20 years ago by Nobayama at 17 in the lower left and 34 gigahertz in the middle. There's the solar limb. There's the soft X-ray emission in color on the right, the hard X-ray footpoints. And this is a really beautiful event. What you're seeing is the glow from MEV electrons, several MEV. These are not 10, 20, 30 keV that are referred to as hard X-rays. These are really highly energetic electrons. And at the end, you'll see an eruption of absorbing material, occulting the flare, and then it disconnects, and you'll see a flash. Bam. So coming back to this cartoon, what you saw with that flare is the soft X-rays in the upper part of the loop, the hard X-ray footpoints, and then here are the sort of loop legs, weighted by the fact that the magnetic field is so much stronger near the footpoints than it is at the loop top. So you see this gradient in, let's call it specific intensity. Here's a couple of sort of interesting little tweaks. Here's an example of a little tiny bipole flare. So total intensity, polarization. You see there's a polarization flip as it goes across this bipolar magnetic field. Light curves at various locations in the loop. At the loop top, B, you see that its peak is actually delayed by a few seconds relative to hard X-rays, which are the prompt signature. And at the foot points, they're delayed, but to a lesser degree. Why is that? The delay, in part, is due to the fact that the electrons are in this bottle, so they're going to build up for a period of time before they start to decline. But another feature is the decay time is also, longer for the middle, the high part of the loop than at the foot points. So what's going on? Well, here are some sort of uniform gyrosynchrotron spectra, very strong sensitivity for the spectral maximum on the magnetic field. So you can sort of think of, if we look at the contribution function producing non-thermal gyrosynchrotron radiation, the maximum contribution depends on magnetic field. So the energy, typical energy for a power law distribution of electrons, the electrons of a couple hundred keV will be producing the most in a 1,000 Gauss field. And as we go down to 200 Gauss, it requires electrons with more oomph to emit at a given frequency, higher harmonics, okay? And so higher energy electrons are involved. So you can sort of think of a magnetic loop in the sun's corona as acting as a dispersive element. Really neat that way. So at foot points, you're looking at lower energy electrons, they precipitate out more quickly, and so they have shorter delay and faster decay. And the ones at the loop top, higher energy, and so longer delay, and they linger a bit longer. And so you can sort of do some simple computations and illustrate that at the loop top, you're seeing higher brightness temperatures, higher effective energy than at the foot points. Another sort of fun fact, there are lots of dependencies for non-thermal gyrosynchrotron, and it's very cumbersome to compute, but they're fast codes now. But it does have an interesting dependence on ambient density due to this phenomenon called Razin-Sitovich suppression, which leads to what might be confused with self-absorption, but it's actually a suppression mechanism that bends the spectrum over and gives you a very nice discriminant on what the ambient density is that these fast electrons are jangling around in. Okay, so putting all this together, with this Pathfinder tool, the EOPSA instrument, the Expanded Owens Valley Solar Array, we're beginning to be able to do spatially or angularly resolved imaging at a wide range of frequencies, measure the brightness temperature spectrum as a function of location and time, and do detailed forward modeling to back out these myriad parameters of interest. So the hope and the dream, ultimately, and I'll show you an example in a moment, is to basically be able to track the spatiotemporal evolution of the accelerated particle distribution and the magnetic field that's implicated in this. Get them both. So here's an example. I think probably all of you have seen the celebrated flare of 2017, September 10. It was sort of a theorist's dream because this enormous flare, flux rope eruption, fast CME on the limb of the sun. So a nice ideal viewing geometry. And the background here is AIA EUV imaging. The lines here are sort of the Linen-Forbes analytic model for a flux rope. And you can see the emission here in radio, sort of these outlying low frequency sources, and then the source associated in the sort of aftermath of the eruption of the flux rope, which has been interpreted in terms of a current sheet. Now we can argue about this at length, about whether this was grossly overinterpreted or not, but it was a sort of a concept demonstration of inferring the magnetic field using this sort of forward fitting to the spectra as a function of position, measuring the magnetic field convolved with the instrument response function and comparing it to the model and MHD simulations. And in fact, they agreed remarkably well. So the lines here are the expectations from the models, and the points are the measurements of the magnetic field as a function of vertical axis y. And then this was an estimate of the electric field out of the screen, Vx cross B times By. Okay. So it's got a couple hundred hits in citations already. So it's attracting some attention. And it sort of is a proof of concept of how one might exploit such observations in practice. Okay. Let's move on. This is again, thermal free, but now we're beginning to encounter coherent emission as we get into tens of centimeter wavelengths. Okay. So I'm going to show you an example from the VLA, coming back to this cartoon. We've known for a long time that we have both positive slope and reverse slope type 3 bursts at decimeter wavelengths. So same thing as a classic type 3 that I'll show you in a moment, an electron beam producing Langmuir waves and plasma radiation, okay? And they're thought to be intimately associated with the energy release region. Those escaping upward become type 3 or type 3-like emissions. Those going down, you can maybe see in a spectrograph, and you may see the hard X-ray signatures, they splash down. We used, my student at the time, Bin Chen, was commissioning the VLA for solar, and we observed the sun at 50 millisecond time resolution, 1 megahertz spectral resolution, and 2 polarizations. So that was 20,000 snapshot images per second to look at these type 3 DMs at a flare. And we didn't see a flare, but we saw a soft X-ray jet go off, which is shown here in EUV, and in blue is the radio flux, and red is the 12 to 25 megahertz. So you can see that the type 3s popping off were related to the hard X-ray emissions splashing down. And this is really fun because we can basically measure the trajectory of these type 3s as a function of time and space. So, whoops, nuts. How do I that to go? It was a movie, and as it went across that peak, it was going to show the type 3 DMs, but they do not show up as beams. Oh, there we go. Maybe you can run that. It looks like a thunderstorm. You see little flashes. You don't see sort of coherent beams going out. So it's like, oh, do I need to? Huh. That's too bad. But anyway, if you integrate up over all these trajectories, you end up with that pattern on the left, where red is high frequencies, blue is low frequencies. So the beams are going from high density to low density, and they trace out this sort of cusp-like structure above the energy release site, and below are the corresponding hard X-rays. But what's also interesting about this, in addition to sort of mapping the trajectories of beams in the corona, is that if this is plasma radiation at the fundamental or harmonic, the densities involved are of order 10 to the 10. And there is absolutely no sign of the beams in EUV. And if you go through the arithmetic, you find that the filling factors are very low in order to support such densities, indicating that the corona is extremely fibrous. Okay? You sort of think of this bundle of fibers where the density changes, can change quite a lot from sort of flux line to flux line. All right, let's talk a little bit about meter wavelengths. This is where radio astronomy of the sun sort of had its birthplace, and which is unfortunate because it's some of the most treacherous terrain of all in terms of understanding the plasma physics in detail that produces the bursts that we so often see. So I'm not going to dwell on this. I'll just remind you that, these types of emission were identified in the post-war years in the late 40s into the 50s. Type 1, this bandwidth constrained emission, often highly polarized. Type 3, I'm sure you've all heard of, the electron beams that propagate not only through the corona, but out into the interplanetary medium. Type 2 and type 4 radio emission. Type 2 believed to be driven by MHD shocks in the sun's corona, low Mach number shocks. Type 4 is sort of an aftermath emission. I don't like using the phrase type 4 because it's a catch-all for almost any post-flare emission. And then type 5, you never really hear about very much anymore. But I would say that the state of the art in terms of understanding the detailed plasma physics for each of these is not in great shape. So if you're looking for something to do, another thing though, which is a little bit more recent, is the detection of synchrotron radiation now from coronal mass ejections, so radio CMEs. So fast electrons are entrained in the magnetic field of the CME, and if it's synchrotron radiation, you can in fact, again, sort of forward fit the spectra and deduce, ambient density in the magnetic field. As far as I'm aware, other than Faraday rotation, it's really the only way to try to constrain the magnetic field, other than in situ measurements as well. So we found, sort of 1.5 Gauss out to about 1/3 of a Gauss from 2 to 3 solar radii. Here's another example from Maya. This is at 421 megahertz. Another fast CME, another big SEP event. And more recent work has been using low frequency telescopes, sort of 70 to 300 megahertz, or the 15 to 85 megahertz telescope, and they're beginning to see more and more of these radio CMEs. I'm finding these examples pretty interesting because they're actually quite intense. 10 to 100 solar flux unit, 1 million Janskis per beam. Okay, now let's go above the ionospheric cutoff into outer space because we can't see these long wavelengths on the ground. And really, the only emission we can see are these coherent radio bursts. The sensitivity is not there to see anything but coherent bright emission. So again, this has a long and storied history. It dates back to the 70s. The Voyagers, IC3, Wind Waves, Ulysses, Stereo, now Parker, and Solar Orbiter all carried radio spectrometers. Operating, you'll see the frequency range here is sort of from 13 megahertz all the way down to tiny fractions megahertz. In fact, Voyagers, I'll show you, goes all the way down to kilohertz. Kilohertz is kilometer wavelengths. So, this example here is from a catalog of Gopalswamy and colleagues showing type 3 and so these are the type 3s, sweeping from the corona out into the interplanetary medium, the associated type 2 that is connected to this fast CME here. But what's really interesting, so this has been going on for a long, long time, but what's interesting in the past, decade or more, is that we now have multiple missions active at various locations inside 1AU typically, but Ulysses, of course, is outside that. And we have ground-based instruments at low frequencies as well. So you have multiple vantage points to look at these radio bursts as they go sweeping out into the interplanetary medium. So you can do triangulation, and as I'll show in a moment, you can begin to look at use them as beacons and try to understand the medium between you and the spacecraft or the ground-based instrument, as the case may be. Here's an example from a nice paper by Sam Badman and colleagues using both ground-based instruments and space-based instruments, Stereo A and Parker Solar Probe plus LOFAR on the ground. And you can see here the multi-frequency source from the ground using LOFAR from 20 megahertz up to the bottom of the FM band. You can sort of determine then the 3D and then use the spacecraft to sort of define the trajectory of the Type 3 as it goes further out in 3 dimensions. This was the Type 3 in question observed by the different spacecraft. Okay, finally, for the heliosphere, there's this fascinating phenomenon that was discovered back in the 80s by Voyager as they approached the very boundary, the heliopause of the solar wind. They found that there was this emission, and you'll see that it's sort of 2.5 to 3 megahertz, or kilohertz. Okay, that corresponds to a plasma density of about 1 particle per 10 to 20 cubic centimeters. Very dilute, it's way out there. And then it went away. And then it reappeared a solar cycle later, an activity cycle later. And then again, okay, so what's going on? Well, it's sort of the idea, and it's still somewhat controversial, is that, that they sort of tried to attribute it to a single big event, say the Bastille Day flare, propagating all the way across the solar system and colliding, shocking and colliding with the outer boundary of heliopause. Or it's sort of a super shock that it's a shock as a result of sort of the accumulation over a period of time during a maximum period that sort of piles up and eventually, like a wave breaking, lands on the heliopause beach, generating sort of like a standing Type 2 plasma radiation at the plasma frequency corresponding to these very low densities around 2 to 3 kilohertz. But the story is not over. I mean, in 2012, it's thought that Voyager 1 left the solar system and eventually entered pristine interstellar space. And then in 2018, the same happened with Voyager 2. And what's kind of mind-boggling is we continue to see these sort of pulses of radiation. Somehow, these solar events or mega merger events pulse out into the interstellar medium. So that's boggles my mind anyway. Okay. Finally, let me just sort of advertise a mission that's currently on the ground, launch imminent, we hope. It's, it's all bag tagged, ready to go. Little microsats, 6 of them, forming a mini VLA up in space to finally begin approaching the problem of imaging radio bursts in space with higher angular resolution. So instead of doing direction finding with a rotating spacecraft with a 100-meter antenna, having these little tiny apertures that cross-correlate and give you information on location, trajectory, angular width, and so on as a function of time and frequency. So that's pretty cool. It's called Sunrise, and the emphasis here is on imaging. All right, let's go to part 2 in the little bit of time I have left. All right, we're going to turn things around, as I mentioned, and consider, well, okay, so how can we use sources of radio emission to probe the foreground medium? And by foreground medium, in this case, I'm going to focus exclusively on the solar wind and the corona, not planetary atmospheres and ionospheres, although that has been done as well. So we've just talked about radio bursts. You can use a radio burst in the corona or the IPM, and the signal propagates to some receiver, and you can try to determine, using properties of the emission, for example, its decay time or something else, on how the intervening medium may have affected that propagation. But you can do lots of other things. You could use a spacecraft beacon. That's been done many, many times. You know, Soviet Venera, Mariner, Messenger, Ulysses, lots of spacecraft with a coherent beacon. By coherent, I mean sort of monochromatic, essentially. And you see how the medium messes up that signal, spectral broadening, for example. You can even use radar. Bill Coles and John Harmon transmitted from Arecibo, bounced off Venus for a double pass through the medium. Pretty cute. Or we can just use cosmic sources. We've got lots of, you saw Craig's stars in the background of Punch. That's what the sky looks like at radio wavelengths. Most of it is galaxies, not stars. They're very, very far, so they're fixed on the celestial sphere. And as the Earth orbits the sun, sort of the background of sources that you can see with the sun in the foreground changes, and you can use many of these that are point-like to probe the foreground medium. So I'll show you an example first of using radio bursts to say something about the medium. And then I'll say using the tools of statistical optics to use cosmic sources, okay? More busy slides. Again, read these later if you want. Okay, there is one dispersion relationship for electromagnetic radiation in a plasma. You can work out the refractive index. The group velocity is going to be less than the speed of light for photons in a plasma. You can express the fluctuating part of the refractive index due to inhomogeneities in the medium in terms of fluctuations in electron number density, okay? And you can sort of describe the statistics of these fluctuations in terms of two-point correlation functions, okay? So there's an example of how two-point in refractive index relates to two-point in density. And if you have a nice statistically homogeneous isotropic medium, take the 3D Fourier transform of the two-point correlation function, and you get your spatial spectrum of these fluctuations. Okay? The early days, again, this has been used for a long, long time. Early days, people didn't know much about the nature of the solar wind. They assumed a Gaussian correlation function with a single scale. You can, going back to good old Chandrasekhar, work out what the mean angular deviation is due to interaction with an inhomogeneity. Monte Carlo techniques were used for many years, and you can sort of express the discretized version here, where you see that the scattering over some step is proportional to 1 over mu to the 4. If we're talking about plasma radiation, mu is going to be close, we're close to the plasma frequency, and so mu is going to be very small, of order 1/10 or something. So this is going to be a very large magnifying effect in terms of how the radio waves propagate away from the source. And also you see that there's this epsilon over h. Epsilon is delta n over n. It sort of captures the nature of inhomogeneities and their scale in the medium. So that was the early days. We know a lot more now, and the sort of ray tracing and has been sort of recast in terms of stochastic Fokker-Planck equations. And here's a couple of more recent publications. Edward Contar and his group at Glasgow have been using this a lot recently. We now know that the correlation functions are not Gaussian. They're often parameterized in terms of a power law with an outer scale and inner scale. And you can have an effective H, which is 1 over this spectrum weighted wave number Q. And this sort of illustrates the diffusion of photons to some distant screen at 1 AU. And taking moments of that distribution, you determine the angular width and the position. So this has been used now for several years using these multi-point, multi-spacecraft vantage points. Here's an example from a paper by Krupar in 2020, which used stereo A, Parker, and wind. Here's some type 3s observed, and you see that they're displaced from one another in time because of these, first of all, just even if there was no medium at all, because there are different locations, distance over velocity of light. But in addition, there's the propagation problem. And so they focused primarily on decay times as a function of frequency and used the Monte Carlo calculations to deduce what the degree of inhomogeneity. This delta n over n is in the solar wind and how it evolves with radius. Okay, and so their prediction for Parkers, you go in to 10 solar radii, say, it's given by the orange boxes, and it's kind of a surprisingly high value of about 36% with this 1 over square root of r dependence. Okay, that's just an example. Okay, yet more preliminaries. But I think this is the last slide of lots of text. But okay, I mentioned the group velocity. If you compare the time it takes for, photons in vacuo to traverse a distance delta z, it's just, 1 over c basically, delta z over c. But if it's traversing a plasma, you have this refractive index coming in, and you get something called the group delay because it takes longer for the ray to propagate across the slab. Or you can do it differentially. You can look at one frequency and another frequency because you have this wavelength square dependence. Higher frequencies zip through faster than low frequencies. So this has been used. So using Ulysses, actually, as it went behind the sun, they looked at the change. You see that the dependence on the so-called dispersion measure is just given by this line, this integral over electron number density. So you're just integrating through the corona. And as you go in behind the sun, you see the density go up, 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 up. As you measure the group delay, differential group delay. And then during egress, it comes back down again. So a really nice, clean, direct measure of the sun's density, electron number density. Okay, well, it's what's also kind of nice is that if you, again, have this slab of plasma, the phase of a wave incident on that plasma is going to change. Because if you count number of wavelengths across, it's going to just be, again, delta z over lambda in vacuo. But for a plasma slab, it's delta z times refractive index over lambda. In effect, a narrower slab, smaller number of wavelengths. And so this leads to a delta phi, delta change in phase, is also related to sort of the slab and the fluctuation in electron number density. So what this does is it sort of ties phase to electron density fluctuations. Okay, and a useful statistic, as I'll show in a moment, characterizing phase statistics is the so-called wave structure function, which is given on the bottom here in terms of phase and the autocorrelation, two-point correlation functions. Oh, there's an example actually of a pulsar observed through the interstellar medium from high to low frequencies. And you see that the pulse is delayed as a function of that plasma along the line of sight. Okay, so what the pulsar people do is they want more signal to noise, so they coherently de-disperse the signal to line everything up and then co-add and get nice high signal to noise to do. That's shown on the right. Okay, I'm going to now segue into the last part of it, well, the next to last part of the talk, namely using these phase statistics to learn something about solar wind or the corona. And I'm trying to sort of give you some intuition as to how this works. If we think of a background source, quasar, way far away, the incident radiation is just plane waves. You have the solar wind, what we're going to think about as a thin phase changing screen. And so the plane waves, the phase is changed in a transverse dimension. And so what comes out is this corrugated wavefront. And if you think of the direction of the radiation now incident on our telescopes down below, is the normal to that wave locally. So you gather up these vectors here that are perpendicular to the local wavefront, and you get this angular distribution. In other words, the source viewed through this turbulent screen has broadened out the emission. Okay, does that make sense? Okay, once we have broadened our source from a point source, you can actually, I'll leave it to you to demonstrate that, in fact, if it was a delta function point source incident, like a pulsar, say, you're also going to see temporal broadening because you have multi-path propagation now. So some paths are longer than others. And also, in the case of the solar wind, it's propagating out at some speed. V sub SW. And that leads, if you have a coherent signal, monochromatic signal, leads to spectral broadening. So you can use all of these sort of second moment effects to learn something about the foreground medium. And the example I'm going to show you is using angular broadening to do this. I'm not going to really dwell on scintillations, that's sort of fourth moment statistics, because you're correlating intensities, and the intensities are electric field square, so fourth moment in electric field. But I'm sure you've heard about IPS, interplanetary scintillations, or ISS, interstellar scintillations. Basically, incident wave is scattered by an inhomogeneity of size d into a diffractive cone. These propagate down to the ground. They constructively and destructively interfere, producing variations in intensity. And now, since the solar wind is carrying this diffraction pattern across your telescopes, you see variations in intensity as a function of time. And in the so-called weak scattering limit, you can actually measure the time series, make a power spectrum. It has a characteristic shape. The physics and optics are a little bit complicated, so I'm not going to do that. But you can deduce properties of the solar wind spatial spectrum as well as solar wind velocity. Or you can even do something as dumb as two telescopes separated, let the diffraction pattern sweep over them, measure the time delay, and you have the solar wind speed. One other effect, propagation effect that's been important is Faraday rotation. I didn't really talk about polarization, but if you have a linearly polarized signal from a spacecraft or from a distant galaxy, they can be linearly polarized. As it propagates through a magnetized plasma, this line of sight integral comes into play. Basically, the line of sight magnetic field times the electron number density. That's called the rotation measure. You can constrain that using Faraday rotation measurements. And furthermore, looking at fluctuations in the Faraday angle change, this delta chi, you can say something perhaps about plasma waves, or Alfvén waves in the magnetic field in the medium. So there are lots of different phenomena, and this is not a complete table that you can use, 5 minutes, okay, that you can use to learn things about the solar wind and the corona. Okay, I probably won't have too much time to go into this. I'm going to say a few words about angular broadening and solar wind turbulence, and then if I have time, I'll mention Faraday rotation as a probe of CMEs. So, you know, schematically, if you make a spectrum of the magnetic field fluctuations, you sort of get this canonical spectrum down here at 1 AU, energy containing scales, inertial range of the Kolmogorov type index, and a break scale that is interpreted often as a dissipation scale. I'm showing a structure function up here, but sort of think of it as a spectrum flipped around the y-axis. On the largest scales, it's actually Kolmogorov-like, its dependence on S, 5/3 slope. But then unlike, say, a magnetic field fluctuation spectrum, at intermediate scales of tens to hundreds of kilometers, it flattens out. And then again, at the smallest scales, it's believed to break down. And this sort of canonical spectrum was worked out in the 80s and 90s. But I would say not much work has been done on it since in terms of understanding. What's interesting, though, is if you extend the Kolmogorov portion down, you see that you have an excess power in electron density fluctuations on intermediate to small scales. Quite large, in fact. So, you know, there's a lot of work that still remains to try to understand the evolution of the spectrum with distance from the sun, the latitude, the wind type, secular variation, and so on. What's responsible for the spectral flattening? I mean, Ben Chandran published papers some time ago, 15 years ago, suggesting it may be onset of kinetic Alfvén waves, which are compressible. Yeah, maybe. All right, let's ignore the arithmetic. Basically, it turns out the structure function is related to the spatial spectrum. And that first line there, the phi sub n is the spatial spectrum of electron number density fluctuations, and d sub s is that phase statistic that I mentioned. Complicated arithmetic for a fairly simple function that has these two asymptotic limits, s to the alpha, alpha the index on the turbulence in the flat portion of the spectrum when you're above the dissipation scale, and it just is a simple square law below that, okay? So we've done some observations during 2019, during the third perihelion, minimum corona. All those dots refer to background sources that we measured angular broadening. With the VLA, that's what the instantaneous number of Fourier components are that we're measuring in 2D, okay? And up here in the upper left is what the visibility amplitude is as a function of sort of spatial scale. And it doesn't look very clean, it looks kind of messy, but if you do the inverse Fourier transform and make an image, that's what the source looks like. That's the scatter broadened source. So that's nice, but you'll immediately notice it's anisotropic. Something about the turbulence means it's scattered more in one dimension than in the other. Well, you can do the fitting, and it's convenient to fit for the data in the visibility domain. And once you sort of solve for the coherent scales in the parallel and perp dimensions, correct for refraction, and normalize the data, you get this nice, beautiful visibility curve. And multiplying it, taking the log and multiplying by -2, you get the structure function. And there's the structure function. You can fit it to this hypergeometric function and deduce an inner scale. You deduce it alpha. You have a confusogram to the right there. I'm not going to go into it, but notice all the little blue lines. That's the orientation of that anisotropic source. Basically, the inhomogeneities are elongated along the magnetic field. And so they're sort of ellipses perpendicular to the magnetic field. And if you sort of look at those, they're mostly radial once you get out 2 to 3 solar radii. And you saw that from Craig's images of eclipses this morning, that the field is essentially radial after you get out from the inner corona. Okay, I'll just show you this one, which is basically this epsilon delta n over n in aggregate integrating over the spectrum. You'll see as a function of radius, it's kind of constant, sort of few percent up to maybe 10% with a position angle dependence, lower above poles because the density is lower, higher above the equator. But you see that it falls off inside of 5 or 6 solar radii. We can talk about why that may be. I don't know really, but maybe. Okay, that was one example. And let me finish in the last minute. Faraday rotation. Again, this has been used for many years using spacecraft beacons. This nice paper by Patzold back in 1987 established the envelope of this rotation measure in the sun's corona, from which they were able to deduce the run of magnetic field strength along the line of sight towards the source, towards the spacecraft between 2.5 to 10 solar radii. And I still think it's a pretty good standard. Liz Jensen and her advisor did some work using the Messenger spacecraft beacon to suss out what a magnetic flux rope might look like in Faraday rotation. And so they sort of did lots of model calculations, and this very nice paper by Brian Wood a few years ago used some ground-based observations of a polarized radio galaxy, the 2 lobes here, and multiple vantage point stereo observations of a CME to model the CME and the pierce points of the background source through it to do a pretty nice job modeling the variation of rotation measure across the flux rope as it passed through the line of sight. So I recommend that paper. And that's it. Thank you.
The then kinetic Alfvén waves as to why the spectral breaks in the structure function differ from the turbulent cascade, the typical Kolmogorov, especially in the inertial, like transitioning into the inertial range.
You're referring to what has been interpreted as a dissipation scale?
Yes.
Well, first of all, it's an outstanding problem. I mean, I don't think the physics of dissipation are understood. I'm finding that the scales across this limited range of sort of 2 to 3 to 10 solar radii, it's most consistent with an ion inertial scale, not an electron cyclotron scale. That may be a hint. Marco is probably the one to address that more comprehensively. I mean, I was very pleased to see evidence of breaks in the structure function because in previous years, people hadn't found it. And most of the information was coming from spectral broadening type experiments. Reassuring that different techniques were giving comparable results. Austin.
I forgot the name of the mission. Is it the Sunrise mission?
Yes.
What's the effective aperture size when you have them spaced out?
Well, it's going to be variable as they drift apart. I think it is going to have limitation of 10 to 15 kilometers separation, which is not very big, right? So they'll let them drift apart and then stabilize them, but they'll sort of drift around. But it's a little easier to manage all this stuff, the timing, the correlations, and so on, because we're operating at such low frequencies. And in terms of wavelengths, number of wavelengths across 15 kilometers, it's not a big stretch technically.
Thank you.
Thank you. Very nice talk. I got a question. When you showed the how you measure the solar wind properties, where you had these incoming plane waves, and then passing through the solar wind, you had these perturbations, right? Like these phase errors in the waves. How do you make sure that these phase errors are coming from the solar wind and not from other sources, for example?
Well, first of all, we look at a spatially coherent source, just a point source of known flux density. So we normalize by the flux density, and so we have a unit beacon. And we image it for calibration purposes when it's far from the sun, many weeks before it gets anywhere close to the sun. So we sort of check for any perhaps extraneous radio lobes or something like that. And for a few of these sources, there were extended emission, but for the most part, they're all point-like. And so, yes, then we look at them again at very small elongations to the sun. At the wavelengths available at the VLA, we can realistically only go out to about 10 solar radii. Otherwise, we need to go to yet longer wavelengths because you may have, it went by fast, but the structure function had a wavelength square dependence. So that's nice in the sense that we can get closer and closer to the sun by going to shorter wavelengths, higher frequencies. But in the VLA, it only goes down to 1.2 gigahertz, 30 centimeters roughly. And so we need an instrument to go to yet longer wavelengths. We used to have so-called P-band, which was 90 centimeters, and that's not well suited for this work in the sun. How do we know that it's the solar wind and not something else? Well, it's not going to be the ionosphere because in the case of the ionosphere, the refractive index fluctuations are not going to be very strong. They're not going to produce scintillations or angular broadening. For one thing, the screen is right down on top of us. So it's not going to have any significant effect. We do have to worry about the ionosphere for Faraday rotation measurements. The total electron content through the ionosphere can foul things up, especially during solar maximum when it can be variable. And some of these observations do take time. You have to integrate up. Dominant contribution has to be the solar wind. Thank you.
What are the challenges to upgrade existing facilities like Nobiyama with multiple antennas to perform multi-frequency imaging? So why do we need another instrument instead of upgrading for multiple frequencies, the existing one?
Well, you're familiar with EOPSA because you're at NJIT, and they use basically log periodic dipoles to see across the large frequency range. For little tiny dishes like those at Nobiyama, which are only 80 centimeters across, you have to have a feed that's small enough so as not to obstruct the field of view, which means you're restricted to short wavelengths, high frequencies. And so it's a shame that they had to shut it down because perhaps, they had, instead of 17 and 34, you could have a little log periodic or sinuous feed to do at least an octave of bandwidth, say 17 to 34 continuous. But if you want to do very large, like decade or more wide bandwidths, you have to have enough real estate to have a substantial feed, because the feed, roughly speaking, scales with wavelength. So if you want to go down to 30 centimeters, you need something pretty large, and you can't put that on a little tiny dish.
From initial design, that's kind of.
Well, so for example, this instrument that we've been chasing for a number of years, Phaser wanted to do broadband imaging from sort of 50 megahertz up to 30 gigahertz, really broadband. You can't do it with one system, one aperture size. You have to break it up into subsystems of 2-meter antennas to service the high end, intermediate size 5-6 meter antennas to do the decimeter to meter wavelengths, and then maybe log period. Basically, the image I showed you of MWA or LOFAR just use tiles of dipoles that you phase up, and they serve as an antenna. Yeah, it's interesting. Great. Thank you.